Good evening, everybody. So, we will just still continue the higher coordination numbers, and we were with some octahedral geometry, and there we are just talking about the two types of distortions. One is tetragonal distortion and another is trigonal. So, in case of tetragonal distortion, what we see that we are focusing our attention on a tetragon, that means the plane which is the square plane, which contains 4 ligands and 2 other ligands in the octahedral situation. One is above the square plane, another is below the square plane. But when we talk in terms of the trigonal distortion, we will be focusing our attention on the corresponding trigonal planes, because one particular octahedron can have 4 such corresponding tetragonal planes. They are mostly in 3 directions along the 3 Cartesian axes x, y and z. So, we can have both the elongation and compression along the tetragonal axis, along x, along y and along z. So, we can have elongation as well as compression along x, elongation and compression along y and elongation and compression along z. Similarly, in a particular octahedron we can have 8 such trigonal faces, and along these trigonal faces, which we will consider along the axis, which we will consider as the C3 axis. So, along the C3 axis, how the corresponding elongation and compression and distortion can take place, that will all be known as the corresponding trigonal distortion of the octahedral geometry. And in this particular case, when we are focusing our attention on the C4 axis perpendicular to the plane of the square planes, we will call him then as tetragonal distortions. So, in this part of this lecture of this coordination number 4, we will see that this already we have seen that along this axis, that means this is the original side, the green and the corresponding colored sphere is that this is the corresponding. So, when they are elongated, these are the elongated positions. So, this is the original position basically. So, this is the original octahedron. When they are compressed along these 2 directions. If we consider these 2 directions are z axis, we call that you have z axis compression and your octahedron is typically distorted, and the corresponding metal ligand bond lengths along these axes are less compared to the other axis. But in this particular case, in the second situation, so these A and B both are tetragonal distortions. We also call them, we also label them as D4H distortions. But the second situation, that means the situation C and D, they are called at rhombic distortions and trigonal distortions. The second situations what we are talking about is that along the trigonal plane, this is the C3 plane. This is another C3 plane. So, we have above these we have 4. So, if we just focus our attention at this particular point, altogether this is the meeting point of 4 trigonal planes above the basic square plane, and this is also another meeting plane where we have the 4 trigonal planes are coming. So, we have this, if this is getting elongated along this C3 axis, we get trigonal distortions, and rhombic distortions are such that we have the compression along z axis, elongation along y axis. So, z axis will remain untouched. So, in this particular situation where we consider that when all x, y and z, all these three axes are same, we consider them as corresponding situation is isotropic in nature. That means all the ml distances, we have 6 distances. So, distances along the x axis, distances along the y axis and distances along the z axis. If they are all same, we get a situation where we consider that all the ml distances are almost same. So, we get a regular octahedral geometry, but this is not true always. So, we can have that x is not equal to y, not equal to z. That means, we have, when we have this situation, that means how we get that, we have x is equal to y is equal to z. When this situation is there, we do not have any other distortion. So, in one axis we have, say, along z axis we have compression, along x axis we have elongation, and y remains same, and y is not changing. As a result, what happens that x is not equal to y and y is not equal to z, we get rhombic distortion, and this distortion is known as D2H distortion. The symmetry level is D2H, and we consider this distortion as D2H distortion. So, this is the situation where we have the D2H distortion in figure C. So, if we have the distortion along the trigonal axis, we get the corresponding complexes which are not octahedral in geometry. We get a corresponding trigonal prismatic complexes, and this type of complexes are really not found very much in number. They are rare and mostly found in solid molybdenum sulfide and tungsten sulfides. So, when these sulfide groups are packed around molybdenum and tungsten, they are getting a geometry where the coordination number is 6, but the corresponding geometry is not the positioning of regular spheres like molybdenum spheres and sulfide spheres in a octahedral geometry, but they are placed in a trigonal prismatic geometry. A trigonal prism is also found in other types of complexes which are dithiolane type of ligands we consider, like xanthate and dithiocarbamate. These are dithiolane compounds where we have the backbone CC backbone and 2 thiol units are present. So, it is a bidentate SS ligand. When 3 such bidentate SS ligands are bound to the metal center, we get a trigonal prism geometry. So, we get that situation where we have the sulfur groups, and this is a different type of bidentate ligand. And this bidentate geometry, when it is bound to the metal center, we get in this form, where we find that this sulfur is there and this sulfur is there, this is there. So, if we just consider the top plane, so top plane is like this. So, this is a trigonal plane and the bottom plane is also a trigonal plane. So, this is the first bidentate ligand, this is the second bidentate ligand and this is the third bidentate ligand. So, overall the geometry is like this and we should also be able to draw it nicely, like drawing of the octahedron. This is the trigonal prismatic structure and we have the metal inside, and which is completely different from the octahedral geometry. So, we see that when we have MS2C2R2 molecule, which will be in the trigonal prismatic geometry, and the symmetry level for that would be D3H. It is not a octahedral geometry, it is D3H molecule. So, this is one trigonal face and this is the other trigonal face at the bottom, and 4 other are square plane. So, 3 of these ligands over here and 3 other ligands on these other 3 coordinates. So, few more examples of these are of this type, where zirconium 4, hafnium 4 of this group and molybdenum in group 6, molybdenum 6 and tungsten 6. This we are discussing about the MOS2 and WS2 molecule. So, we have trigonal prismatic environment where molybdenum is surrounded by 6 sulfur groups. Here tungsten is also surrounded by 6 sulfur groups. Similarly, here also the methyl groups are there which are small there. So, metal methyl, so metal carbon bonds are there. So, metal methyl groups are there and 6 such methyl groups surrounding hafnium and 6 methyl groups surrounding the zirconium, also giving rise to trigonal prismatic complexes. So, other example is that is the rhenium complex, and rhenium complex instead of CR3 molecule, now CF3 is another possibility for the ligand system on the diethylene backbone, and that diethylene backbone is also giving again this particular coordination, but when we draw in this particular geometry, occasionally we will think in this fashion that it is a octahedral geometry, but is not octahedral. When we draw like this, is a typically trigonal prismatic geometry. Similarly, again another malonitrile trifluoromethyl diethylate of rhenium compound is the tris compound of this one. In another geometry is this when we showing the corresponding trigonal prismatic geometry. So, trigonal prism, this is the corresponding trigonal prism, and when the trigonal prismatic geometry is available and the binding of these 3 ligands are like this, we get the corresponding compound in this particular geometry. So, this is another form and is taken from some journal paper. This is Inorganic Chemistry 76 paper, where we see that this particular geometry where we get this for the corresponding niobium compound, and where we have the niobate compound. So, D is the rhenium compound. So, this is the trigonal prism, A is the trigonal prism, basically the trigonal prism geometry, and this is when we just rotate the top plane. When we rotate the top plane or we rotate the bottom plane clockwise or anti-clockwise, we get the corresponding trigonal antiprism geometry. So, trigonal antiprism geometry is the corresponding octahedral geometry. So, when we view the situation through this particular trigonal plane, we basically get 2 geometries together. That means, if we just compare the octahedral as well as trigonal prismatic geometries together, we should see through the molecules through these trigonal planes. One is trigonal prismatic and this is trigonal antiprismatic. So, another name of octahedral geometry would therefore be trigonal antiprismatic. So, in the this particular case in the molecule like C and D is the corresponding rhenium compound. This is the whole detail of this, and it is the corresponding positioning of the 6 sulfur atoms in a corresponding trigonal plane prism. So, this is one trigonal plane and this is the second trigonal plane on the back side. And the last example is the corresponding niobium compound, which again hydrogen atoms are not shown, and in this particular case also we have two trigonal planes, one after another, and they are in eclipse geometry, giving rise to a corresponding trigonal prismatic configuration. Then we move on to the coordination number of 7, and from here basically we have a corresponding difficulty, because up to a coordination number of 6 and from a very regular geometry of octahedron, we can consider that how the 6 groups are surrounding a particular center of metal ion with 6 ligand groups, and we have a corresponding octahedral geometry. But when we move to a coordination number of 7, basically what we can do, we can add one more ligand. So, is basically a spherical arrangement, is a sphere like arrangement. So, it is highly symmetric sphere like arrangement. So, how to put the extra ligand? The coordination number 6 would be equivalent to 6 plus 1. So, how we put? So, if all the positions are symmetric in nature, so preferentially we should take one such position such that we put one extra coordination, one extra ligand to get a corresponding coordination number of 7. So, let us see how we put that particular extra ligand, and when we put that extra ligand, we have 3 geometrical possibilities, and which are not common for the first row element, because we need some bigger atom, bigger metal center, such that we can put more than 6 number of ligands surrounding this particular center. So, they are seems to be small and distortions occur, so the prediction of the closest idealized shape is generally difficult. So, these are the situations, these are the 3 situations for a coordination number of 7, where we have added one extra position over here to the octahedral geometry, one extra position over here to a trigonal prismatic geometry, and this is one other situation where we change the corresponding square plane from a square geometry to a pentagonal geometry. So, these are only 3 options we can have. One is known as capped octahedron, and the symmetry level is also changing. It is changing from OH to C3V. Capped trigonal prism. So, we are capping one particular face. This is the trigonal face we are capping. This is the square plane we are capping, which is known as capped trigonal prism structure. And the third one is the pentagonal bipyramid structure. Instead of a square plane, we have a pentagonal plane, and above we have one ligand and below we have one more ligand to give a coordination number of 7. So, the first example, if we can see with that of our capped trigonal prism structure. So, already these green spheres, if we can have, so we have 6 such green spheres in our hand. So, the coordination number using 6 such green spheres are 6, and we put the corresponding additional ligand, that blue ligand, as the 7th coordination. So, if we go from this particular square plane, so we are capping this particular square plane, this particular face of the trigonal prism by this extra donor atom, and we are capping from this side. So, it will be known as a capped trigonal prism capping from the tetragonal face. Then we can have capped octahedron, where we have this regular octahedral geometry connecting all 6 positions and the sphere arrangement. And if we can cap one particular trigonal face by another atom, the another ligand atom, we get a coordination number of 7, and the positioning of all 7 would be like this. So, these 3 and these 3 are for the regular octahedral geometry, and this one is the corresponding extra. So, example for these 7 coordinated molecules are like this. When we have this capped one, this particular one is the capped one. So, tungsten surrounded by 4 carbon monoxide ligands and 3 bromine ligands will give rise to this particular geometry where one particular face is being capped. So, 3+3 situation is well known to us, it can be visualized nicely also, that it can be either in one particular face or it can be through some meridional plane. So, 3 of one type, that means the Beer ligand, and 4 of another type, that means 3 from the other sides and 1 extra, giving rise to these 4 carbon monoxide ligands. Then we can have the pentagonal bipyramidal geometry, which has a symmetry level of D4H. So, we have the pentagonal plane, one above and another below. So, these are the corresponding donor points in the plane, and one above and another is below the molecule. So, this is one particular situation where we can have this, where we have one particular plane is occupied by 2 such ligands of these. So, they are of same ligand, which is a tridentate ligand, nitrogen phosphorus bearing Np2 type ligand, is a tridentate Np2 type of ligand. In one half it is just coordinating through one phosphorus, nitrogen and phosphorus. So, this ligand is fully coordinated to the uranium center, is a diuranyl like molybdenal and vanadium molecule, and the other ligand is not coordinating through this phosphorus, it is only coordinating through one phosphorus and one nitrogen. That means, it is behaving as a bidentate ligand system. So, that is why the ligand, the organic ligand parts are providing 3 plus 2 5 coordination positions. So, the 5 coordination positions from this particular pentagonal plane, one oxo is above the pentagonal plane and another oxo is below the pentagonal plane. So, this sort of situation can also we can get if we have a ligand system which is pentadentate, deriving from 2,6-diacetyl pyridine. So, this is 2,6-diacetyl pyridine. So, when 2,6-diacetyl pyridine is condensed through some ship base condensation reaction with triethylene tetramine, this is triethylene tetramine. So, we get a corresponding ligand system which is pentadentate, and since it is a typical cyclic ligand, which is therefore can be labeled as pentadentate macrocyclic ligand. So, this pentadentate macrocyclic ligand, when it is reacting with UO2 type of metal center, so it is UO2 2 plus, so it can be uranyl acetate also, uranyl acetate is a well known starting material we use in the laboratory also. So, when it is reacting with UO2, so we have basically the ligand system is N5 pentadentate macrocyclic, which can bind to the metal center through 5 nitrogen atoms. So, now we see that how this particular pentadentate macrocyclic ligand looks like. So, it will be this nitrogen, it will be the second nitrogen, this will be the third nitrogen, fourth nitrogen and the fifth nitrogen. So, basically what we get from here is a situation where we have a pentagonal arrangement. So, if our uranium is coordinating over here, so we get 5 bonds from one plane and this double bond is here and another double bond above and below the pentagonal plane. So, we get a pentagonal bipyramidal geometry where symmetry level would be D5H. So, we get also a macrocyclic ligand where the restrictions are there for this geometry. This is also another type of ligand system where we have restricted our thing is that we have 5 donor atoms in one particular plane, and if it is in iron center, so one will be bound above the plane, another will be bound to the below the plane. If they are thiocyanate, so this is also a thiocyanate complex using a macrocyclic ligand similar to that what we have just shown. And another is that heptafluoroniobate compound. Heptafluoroniobate compound is also a capped trigonal prism structure. So, this capped trigonal prism structure we have to accommodate 7 fluorine ligands surrounding this niobium. So, this is one particular form. Then we have what we have shown just now is the corresponding geometry for the capped corresponding capped trigonal prism structure for tungsten CO4 Br3. So, Br3 in one particular phase, one trigonal phase we have the Br3 units, in another trigonal phase we have 3 corresponding 3 CO units, and one is above this particular phase, that means it is capping. So, this is this particular structure where we have the capping CO is at the top. So, this capping CO will be here. So, below we have 3 Br and we another case we have 3 CO, still we have the 4th CO from this particular phase, though we have some steric crowding. So, we now move on to a coordination number of 8. Above 7 we are just moving to a coordination number of 8. And again in this particular case we have 4 possibilities, and the the corresponding polyhedral levels are getting complicated. So, we should little bit slowly remember all these names, and first of these is the cube arrangement. So, whatever we are just now discussing about the octahedral geometry, which can be derived from a typical cube arrangement. So, if we just see how we can draw a nice cube. So, this is the cube. So, how we can derive a octahedral geometry out of a cube, because we are talking a corresponding coordination number of 6. So, we have one ligand here, another ligand here, another ligand here. So, all the central positions of the 6 faces of the cube. So, if we just connect all them, we get a nice octahedron. So, this is the octahedron what we can have within the corresponding cube arrangement. So, now if we just consider that we have increased, we can increase the corresponding coordination number from 6 to 8. So, we have, instead of the center position of all the 6 faces, now we can have the ligands which are occupying these positions. That means all the corners of the cube, which will give rise to an arrangement which has a coordination number of 8. So, metal will be at the center. So, one such arrangement will be the cubic arrangement, and cubic field is their symmetry wise, which is same, which has a symmetry level of OH also. Then cube is the square prism, like that we are relating the octahedron with the trigonal prismatic structure, but if we go for a square antiprism structure, the symmetry level will be changed from OH to D4D. Then we have the dodecahedron geometry, which has a D2D level and hexagonal bipyramid like that of our pentagonal bipyramid. The pentagonal bipyramid just now we have seen. Similarly, if the plane you have is the hexagonal one, then above we have one point and below we have another point, we get a hexagonal bipyramidal geometry of coordination number 8 with a symmetry level of D4H. So, this are the situations. This is cube structure, this is square antiprism, this is one square and this is another square. So, if we just rotate the top plane, so top plane will be rotated, and if they are connected to each other, we get a square antiprism structure where we have 2 of these faces are square face. Like this face, you have 6 square faces in a cube structure. Here we have 2 of these are square faces, but others are 1, 2, 3, 4, 5, 6 of them are corresponding trigonal faces. So, 6 plus 2 again 8 faces, but our face number is also changing when we move from cube to a square antiprism, and this is dodecahedral structures. So, we have the corresponding one structure there, we get this particular one. So, we have 4 at the top and 4 at the bottom, and we basically these 2 corners we distort. If we move these 2 corners upward and these 2 corners downward, we get this arrangement. So, distortion from a cube also give rise to a dodecahedral structure. So, some examples of this cube structure, how we see. So, these are the positions. So, these all 8 corner positions are occupied, we get the corresponding cube geometry. So, this is lanthanum BPY02 ligand, which are 4 in number, and we just get this particular compound in this form. So, 4 such ligands. So, 4 these ligands will occupy in surrounding lanthanum. So, we have the bidentate ligand here 1, here 2, then here 3, and then we have the 4th one. So, BPY bipyridine, when they are oxidized by hydrogen peroxide, we get BPY O2 ligand. Similarly, the square antiprism geometry can be obtained nicely in this form, what we have seen just now in case of ZrOx whole 4, zirconium tetrakis oxalato. So, we have the corresponding geometry of this, which is square antiprism, and 4 such oxalato ligands. So, this is the first oxalate ligand, this is the second one, this is the third one, and this is the 4th one. So, we have at the top we have the square plane, at the bottom we have the another square plane. So, this is the top square plane, and here you have the bottom square plane, and where we see that the top square plane is occupied by one oxalate this side and another oxalate that side. Similarly, from the bottom side we have one oxalate this side and another oxalate this side, will give rise to the corresponding square antiprismatic geometry for ZrOx whole 4 molecule. Now we see the corresponding dodecahedral geometry. So, dodecahedron we have the coordination number of 8, but the corresponding faces we can have. This is the corresponding pentagon basically. So, this side we have 5, then another side we have 5, 10 plus 12. So, it has 12 faces. So, dodecahedron has 12 faces, the face number is basically changing, number of faces are getting changed, and unlike our square antiprismatic structure, this has no 4-membered rings, they are all 3-membered rings. So, you have the trigonal planes only, no tetragonal plane is there, that is why the number of planes have increased. So, you have the 12 faces present in the dodecahedral geometry. An example is molybdenum octahedron complex. So, this particular molybdenum center is in +5 oxidation state, that is why we have a charge of 3 minus. It can be isolated as its corresponding ammonium salt or potassium salt or sodium salt, giving rise to a formula of K3 Na3 or NH4 whole 3. So, the coordination number of 8, that means 4 cyano groups will be surrounding the corresponding structure in all these corner points. So, this is the corresponding structure. So, when we see the polyhedral structure, it is not always easy to visualize this particular geometry. So, at least this geometry is embedded within this polyhedral arrangement, and this geometry when we have, we can see this particular one. So, we can basically 3 plus 3 6 positions we are seeing over here. So, this 5 from this pentagonal part, this is the entire part, the outside, the periphery of this molecule is the pentagon. So, the pentagonal face is visible, then we have this one particular point. So, we have here also we have the pentagonal face and this is the other one. So, 5 plus 1 6 groups we see, 2 are back on the back side. So, this is the first one and this is the second one, these are also slightly visible, this is the one and this is the other one. This is one more example of a ligand system, how we move from a typical macrocyclic ligand and how we derivatize these things. So, this is well known architectural thing on the ligand design. So, how we can change the ligand design. The ligand design gives us some important clues in our hand, that we have seen that we can talk about ethylene diamine. This ethylene diamine is nothing but a bidentate ligand with a abbreviation of EN. It can go to ethylene diamine tetraacetic acid or all capital EDTA. So, when we are derivatizing this particular ligand, so the ligand denticity, this is bidentate. So, bidentate ligand can be changed to hexadentate. How? It is a very simple thing, we are studying on this because we simply derivatizing these two NH2 groups by the carboxy acid arms. So, each NH2 groups has been derivatized by these two arms. So, 2 plus 2 plus 2 giving rise to a hexadentate ligand. Similarly, if we have a tridentate ligand of NH backbone, which is taken triazacyclanonane, and this triazacyclanonane, which is facially capping tridentate ligand, in the same way, if we can derivatize by substituting this NH group by one arm, another carboxy arm, because these arms are carboxy. Similarly, one arm from here and we can put another arm from here. So, tridentate ligand can again be 3 plus 3 means hexadentate. Similarly, if we can go from a macrocyclic ligand which is tetradentate, which is 1, 4, 7, 10 tetraazacyclododecane. So, this tetraazacyclododecane is a tetradentate ligand bearing nitrogens in the macrocycle at position number 1, 4, 7 and 10. And if we derivatized all 4 nitrogen groups by acetic acid functionality, that means the carboxy acid functionality at all the same positions, we get a ligand which is octadentate in nature and known as DOTA, which is abbreviated as DOTA. So, this is the parent macrocyclic ligand which is tetradentate N4 ligand, derivatized from this arm, second arm, third arm and fourth arm, it become the corresponding octadentate ligand, and it can trap basically that particular metal center, which can give rise to a coordination number of 8, because this ligand is providing a system where the ligand is octadentate. So, is a very useful ligand system which can trap the gadolinium ion, which is the lanthanum. So, the lanthanoid complex can be obtained. So, we have basically 4 negative charge on after deprotonation of these OH of the carboxy groups, and gadolinium in plus 3 oxidation state can bind to this ligand, this DOTA ligand, and one charge will be there, and is a very useful molecule from the medical point of view. It is a very useful reagent for MRI scanning, which is known as magnetic resonance imaging. So, MRI scan can be done with the use of this particular metal complex of gadolinium. So, this is a lanthanide metal complex, is the medical imaging technique. MRI is therefore a special type of medical imaging technique used in radiology to see the internal structure of the body in detail. It is a complementary technique related to nuclear magnetic resonance NMR technique. So, we see the last one, that is the hexagonal bipyramidal structure, where the plane is hexagonal in structure, and we have from bottom one and from top side we have one coordination site. So, this is also a bigger macrocyclic structure. So, most of the time what we see that either we can derivatize the thing, that means if it is a nitrogen based system, we can go for simple derivatization of these nitrogen positions, or we can just simply through some ship based condensation or some other type of tetrapyrrole type of condensation reactions, we can move from this is tetradentate ligand we can put one more nitrogen making it pentadentate. So, now if we want to go further, it's not so easy to make a corresponding this sort of linear chain pentadentate to hexadentate one, because if we make such hexadentate ligand and if it goes to bind the metal center, we can have the corresponding folding within this backbone. But if we can do something that to make the corresponding hexadentate one, we can put some rigid backbone. So, we can have one rigid backbone here, we can have another rigid backbone over here, we can have another rigid backbone over here, then we can connect it. So, it can be a hexadentate ligand. If we have the fixed positions as nitrogens. So, it can be BPY type of rigid molecule fixing over there, or it can be bispirol type of unit, such that we can have two adjacent nitrogens. Idea is that we can have two adjacent nitrogens which are fixed with some nitrogen carbon carbon nitrogen backbone. This is the backbone. So, this would be the corresponding backbone, and that will give rise to some rigid structure. So, we have the hexadentate ligand which is rigid in structure. That means, when we put any metal center, obviously that would be a bigger one. It can be from actinide series, which will be bigger in size. So, we have within this cavity of the hexadentate ligand, the metal ion will be sitting nicely over there, and we have one nitrogen backbone here, one nitrogen backbone here, and one nitrogen backbone here. So, we have all 6 nitrogen atoms which are connected. So, this basically gives us something which can be called as the coordination, because all nitrogen is showing coordination to the metal center. So, hexadentate, the structure is rigid also, rigid, and all the coordinations are taking place in a particular plane. So, hexadentate rigid in plane coordination. Is possible. So, now if we can get one above this particular plane, so this is our corresponding rigid coordination, hexadentate rigid coordination through all these 6 nitrogen atoms of the bis pyrrole unit, and if we have the uranium oxo group above the plane and another below the plane, we get a corresponding hexagonal bipyramidal geometry, which is nicely achieved for a coordination number of 8. Then we have the coordination number of 9, which is 3-facet coordinate centered trigonal prism structure of D3H, and this is the face and this is the one other face, and if all the face centered trigonal prism is there, all the 3 faces, that means all the square faces, this is one square plane, this is another square and this is another square plane, all the 3 are capped, we get 6 plus 3 9 coordination, which is possible for rhenium hydrido compound, rhenium nonahydride compound, which is there and which can be going for the corresponding coordination of this. Rhenium is in the group of manganese. So, manganese, technetium and rhenium. This rhenium center is in +7 oxidation state, attaching to 9 hydride groups, giving an overall charge of 2 minus. So, this is the structure fitting with this particular capped trigonal prism. So, these complexes of higher coordination numbers are basically larger atoms and ions are participating, and they are mostly from F block, and they tend to form complexes with high coordination numbers. And this 9 coordination number is particularly important in the F block elements. If it is true with F block elements, that means the lanthanides or the actinides, it can also be true with the 5D elements. So, this is the 5D transition metal ion rhenium in that series, which can also give rise to a coordination number of 9 when the ligand is very small, which is hydride. The hydrido ligand can give rise to that situation. Then we have a coordination number of 10, which can, we have square antiprism we know now with a coordination number of 8, which can be bicapped, that means 2 of the faces can be capped to give rise to a corresponding bicapped square antiprismatic structure of symmetry level D4D. Similarly, if we can go 1 point further for a coordination number of 11, we can get a corresponding geometry where we have a trigonal prism structure where all faces are capped. The 9 we have seen that 4 square faces are capped, 3 square faces are capped. So, 6 plus 3 9 coordination number, then 2 other faces remaining which can also be capped to give a coordination number of 11. And lastly, we will see, because mostly we will just go most of the cases examples we can have for coordination number of up to 12. So, how we get a coordination number of 12, which is very difficult to visualize sometime, and one well known example is there in our hand, which is the corresponding compound of cerium. Cerium, which is a lanthanide, and this cerium compound, when forming the corresponding compound with nitrate groups. So, how many nitrates we can accommodate around a cerium center, that is our question to think. So, 6 such nitrate groups can be surrounded to cerium center, which is in +4 oxidation state, can be very easily generated from the trivalent compound of cerium, which is cerium oxide. So, C2O3 in hot concentrated nitric acid basically generate the corresponding compound as the anionic form of the corresponding hexa nitratocerium compound, which can be isolated as its corresponding ammonium salt. So, ammonium ceric nitrate or ceric ammonium nitrate sometimes is also known as ceric ammonium nitrate, and organic chemists sometimes label it as CAN molecule, CAN, ceric ammonium nitrate, is a beautiful red colored compound, red powder compound, which is shown here on a petri dish. And this red colored compound can be obtained by this way, and this ammonium salt is also looks like this. So, ammonium salt can be isolated like this, and in this particular case we have a corresponding coordination number of this 12. So, where we have a corresponding geometry, and this geometry we have a typical corresponding cube octahedron, which has also an octahedral geometry where it is derived from a corresponding cube structure. And this a cube octahedral form is that if we can have, because the problem is that we have to accommodate basically 6 such nitrate groups around the cerium atom. So, basic idea for getting that cube octahedron geometry is very simple, that we all know that accommodating 6 ligands around a metal center is through the octahedral points. That means, if we can draw the 6 octahedral points around the cerium center, we get a octahedral geometry which is facing towards nitrogen of the nitrate, but here the nitrogen is not making the bond, this nitrogen. So, all the center, that means these nitrogens facing towards the central cerium is in octahedral geometry. So, they are in octahedral geometry, but they are not forming any cerium nitrogen bond, they are forming cerium oxygen bond. So, these two adjacent oxygen atoms of one cerium group is forming new bonds with the cerium center, making 2 into 6 of such nitrate groups, making 12 bonds to the cerium center in a geometry which is known as a cube octahedron geometry. Thank you very much.